Okay, so today we're going to cover chapter 4 of Strogatz, which is flows on the circle. Now this is a pretty brief chapter, so I'm gonna go through it. We're essentially going to use all of the analysis that we've been using for previously, except we're going to change our domain from the real line to that of a circle. Now, everything is the exact same about how we're analyzing flow, except the flow to be uniquely defined on the circle, this function needs to be 2 pi periodic. In order for the velocity of flow at a certain point on this circle to be well defined, okay? And so let's just jump right in with an example here. So if I give you theta dot is equal to omega, where omega is just some constant, what this corresponds to is a uniform oscillator. So it's uniform flow around the circle. So essentially, we're going to have the flow is just going to constantly loop around, and it's going to do so at an angular velocity, a constant angular velocity of omega. If we want to look at the time that it takes for a full oscillation to occur around the circle, we can observe that delta theta over delta t is precisely equal to omega. And so if we want 2 pi, if we set our delta theta to be 2 pi, then we get that our period of oscillation is 2 pi over omega, okay? So this is what we call the period. Now, this is a much simpler example. Let's do something a bit more involved now. So if we have theta dot is equal to omega plus a sine of theta, okay? Now we actually have some variance with respect to theta. And essentially what this corresponds to, if I just plot on the real line here, exactly how we did before. Let's see if I can do this properly. So I'm going to have something that looks like this. Here's my sine wave. And essentially, I'm still going to get fixed points, but what I need to remember is that this interval is our region of interest from 0 to 2 pi. And everything that occurs from 0 to 2 pi is going to occur like in mirror-like fashion in every other 2 pi interval. So we only really need to consider the region from 0 to 2 pi, where our function is uniquely defined. And then in this case, if I have, like, say, a is less than omega, okay, so here's my a, and then here's omega here. So if a is less than omega, essentially I'm never going to have any fixed points. As you can see, the sine wave is kind of like above the x-axis. And so this is also corresponding to just flow that continues to go around the circle, okay? However, we can see that when theta is at pi over 2, should be pi over 2, and then 3 pi over 2. So when theta is at pi over 2, we can see that the flow is most rapid, okay? So if I define this to be my starting point of theta, here's my most rapid flow. So I'll put like a double arrow. And then the flow kind of slows down near 3 pi over 2. As you can see, the actual value of theta dot is much smaller when the sine is at its minimum value, okay? And so as we lower the f of theta here, which corresponds to shifting omega up and down, as we lower this curve, okay, then essentially we're going to get a saddle node bifurcation precisely when this minimum hits the x-axis, all right? And what's going to happen is this slow region, the flow is going to get slower and slower and slower, and then eventually a fixed point is going to be born when A is equal to omega, we can see that the fixed point will actually be born here in the saddle node bifurcation. And then we can see on our physical diagram, we're going to have something that looks like this. Okay, and so here's my fixed point, which is just popped up as a function of omega equals A here. Here's theta dot. And now, quickly analyzing the flow here, we can see that when theta is going from 0 to 3 pi over 2, here's my 3 pi over 2, it's going to be moving in the positive direction. So we can see that essentially we'll have flow that looks like this. And so this part of the fixed point is stable, and then the other side is unstable. So it's a half stable fixed point. And then as omega becomes smaller than A, so as omega becomes smaller than A, and I'm going to put absolute value just to make sure that the sine curve doesn't dip too far below, right? We're now going to have the full two fixed points here. Okay, so we're going to have this would be stable and unstable here. And so this fixed point that I've shown you above here splits off into two fixed points, the characteristic of the saddle node bifurcation. And we have the first fixed point here, the second fixed point here. And now notice that these two diagrams, so all of the analysis that we've done previously, okay, is like fully valid here. Okay, so you can draw your phase diagram in two-dimensional space, right? And just look at the flow on the real line, and everything should be equivalent to flow on the circle. If you have a 2 pi periodic function. The thing is, it's much easier to view this as flow on a circle because I only can concern myself with that interval from 0 to 2 pi, recognizing the fact that f is periodic, and it gives me a really intuitive kind of way of working with the equation, which is really useful, especially with more complicated examples. Okay, so the last thing I'll discuss about this chapter is there's a discussion of phase locking and basically beat phenomena. Sorry. Okay. So suppose that I have like some fixed signal. Okay. And the example that they give in the book is like fireflies, and you're training the fireflies. You have a flashlight, and I'm going to set the frequency of my flashlight to be some constant number omega, and then the fireflies are going to try and either speed up their flashing frequency or slow down their flashing frequency to match with the stimulus. Okay, and that's this phenomenon known as phase locking. And so if I look at let's call this capital theta dot, this is the stimulus, and then maybe I have little theta dot is equal to the natural frequency. This is the firefly's flashing frequency. So I'm going to take their natural frequency, and then I'm going to add an A sine of big omega minus omega. Okay. So essentially, if this stimulus is flashing faster than the fireflies, then the fireflies are going to speed up a little bit to try and match the frequency of the stimulus. And similarly, if the stimulus is slower than the fireflies, then the fireflies will try to slow down their signal to match with the flashlight. And here, this A is a measurement of how well they're able to entrain with the stimuli. And then this, of course, is the natural frequency of the fireflies. So this is our natural frequency, and this is a firefly. All right, so to analyze this system, what essentially we want to look at is how the difference phi is equal to theta minus little theta, how this difference evolves with respect to time, because we really care about how well are the fireflies actually able to match their signals with our flashlight. And that's something we can test and kind of see if our mathematical model is correct. And so to formulate this differential equation, I'm simply going to take the derivative of both sides here. And then plugging in our values here, we have capital W minus little omega minus A sine of phi. And it's nice that we're able to kind of get this entirely in terms of phi. Otherwise, this would be really gross to deal with. So we have our equation in phi dot now. And now it pretty much just looks exactly like the equation we've kind of looked at a few minutes ago, where this is essentially the difference. I'm going to call this delta omega. This is the difference in the stimuli and the natural frequency. And then A is the ability of the fireflies to successfully like speed or slow down their signal to match the stimulus. And so now, using the analysis we've done before, we can look at this equation and we can say, okay, if this difference in the stimuli and the natural frequency of the fireflies is super large, okay, then we're going to have, here's our delta omega, we're going to have a sine wave that looks like this, and essentially we'll undergo phase drift where the fireflies will never actually become entrained. And they'll keep trying to speed up, right? In this region, they'll especially be speeding up. In this region, they'll be slowing down. But the stimulus is just too fast that they can never catch up with it. And the phase difference between the stimulus and the fireflies is just going to continually increase, noting that it's 2 pi periodic. And then if we just have a small enough delta omega here, or say that A grows large enough, so say the fireflies are very well very adaptive to the signal, and they're very good at entraining themselves to the signal. So essentially, if we really wanted to do the analysis, we could say delta omega over A. Okay, so this is delta omega over A. And if this number is greater than 1, we have this case. If delta omega over A is smaller than 1, this means that the fireflies are effectively able to entrain themselves to the stimuli, i.e. the difference in the natural frequencies and the frequency of the light is not too large for the fireflies to entrain themselves. Then we're going to have a system that looks like this. It's actually going to have fixed points, okay? And these fixed points, here's stable and unstable, these fixed points precisely will correspond to what we call phase locking, where essentially the value of phi, once it reaches this fixed point, will become fixed. And so if we remember, phi is the difference between the angles capital theta and lowercase theta. So essentially it's the difference in the flashing times between the firefly and the flashlight, okay? And notice that when this phase difference will become locked at this fixed point, because phi dot will identically become 0. And so because of that, the fireflies are going to continually just flash behind the signal at this fixed value, but they're going to do so at the exact frequency of the stimulus. And so you've effectively entrained the fireflies to flash at a different frequency, the frequency of your own stimulus. Okay. The last thing I'll mention about this chapter is solving for the period. Okay, so there's kind of a discussion of solving for the period of an oscillation. Okay, so if I have phi dot is equal to f of phi, then essentially to solve for the period, This is a separable equation, right? So I can just write d theta over f of theta is equal to dt. And then, all right, to solve for the period of an oscillation, we're first going to observe that we can't have any fixed points on our circle, okay? So if I have a fixed point on my circle, say I have something that looks like this, it doesn't make sense to start to talk about the period of an oscillation, because if I start at some angle, theta naught, I'm never going to actually return to that angle. I'm just going to approach the fixed point asymptotically, okay? Therefore, we should only consider cases where there are no fixed points, okay? And so the flow could still be non-uniform. For example, we could have a diagram that looks like this, okay? And now we just want to figure out how much time it takes for, if I start at theta naught, how much time it takes for me to fully return back to theta naught, okay? And it turns out that solving for this is as simple as just integrating the differential equation, okay? So if I have theta dot is equal to f of theta, I can separate this equation to give me theta over f of theta is equal to dt. And now I'm going to integrate both sides, and I'm going to integrate the right-hand side with from 0 to time t, which is the period. And then for the left-hand side, I observe that in one period, my angle is going to change from my initial angle to 2 pi plus that initial angle. So I'll just put it like this. Sorry. Theta naught to theta naught plus 2 pi. And then if we wanted to just write this in simple terms, we can observe that this is, I could really just write this as the integral from 0 to 2 pi, because it's going to be identical if I shift the angle by any amount. Okay, so this integral here is precisely the period. All right, and this is really useful because, modern computational apparatuses can calculate this integral for us very quickly and efficiently. Now, there are certain systems where the period is spent almost entirely in a small region. Okay, so if I have, let's say, remember how in the previous example we had a sine wave, and then its amplitude like nearly crossed the x-axis at 3 pi over 2. Okay, and so observe that the flow in the circle, like we talked about before, is extremely slow at the angle 3 pi over 2. And in fact, it's so slow that almost all of the time is spent in this region, okay? And so to estimate the period of oscillation, we can actually Taylor expand about 3 pi over 2, which is basically a ghost of a fixed point, right? It's not a real fixed point because there's no actual root there, but it's very, very close to a fixed point. And so therefore we're going to see this almost ghost of a bifurcation, and we can Taylor expand around the ghost in the second order to get a parabola like so. And then if we integrate this parabola, I'll call it capital F of x. If I integrate capital F of x from negative infinity to infinity, or sorry, dx over capital F of x. So again, if I have the differential equation, x dot is approximately capital F of x. So I want to just approximate my flow by this red parabola, which is the second degree Taylor expansion around the fixed point, ghost fixed point. I can just separate this equation, and I'm going to get dx over f of x is equal to dt. And now I can integrate, and I know that if I want to integrate this time from 0 to tau, and I basically am going to say that the system is going to go from negative infinity to positive infinity in a finite amount of time. And this is precisely my tau here, okay? And then I'm going to integrate this from negative infinity to infinity. So if I look at this integral is basically the amount of time that it takes for a particle if we just look at the flow on the line, and we have this parabola, It's the amount of time that it takes a particle to go from negative infinity all the way to positive infinity. And the fact is that this integral is actually convergent, because notice that in these regions, the particle is going to be moving like exponentially fast, or even more quicker than an exponential, okay? Because its derivative is of the order x squared. And so because of that, it's actually going to like shoot like a light speed rocket across the real line, and do so literally like cover the whole real line in a finite amount of time, which is pretty incredible. And this integral is exactly that amount of time that it's going to take. Okay, and notice that this amount of time is almost entirely spent in this small region. Okay, because that's when the particle actually slows down. So the particle actually slows down in this region, and then outside of that region, it's moving at like light speed, and so it's basically taking almost no time at all to diverge to negative and positive infinity. And therefore, we can say that this integral is actually approximately just the time that we've spent in the bottleneck. Okay, which is fascinating and a super useful idea. And so, if we go to a specific example, let's say we have Strogatz's example of f of theta is equal to omega minus a sine theta. Okay, and this example is slightly different from the diagram I drew above, because we have the negative sine theta, so our bottleneck is actually going to occur at pi over 2. So if I want to estimate the period for this system, I'm going to expand around the fixed point pi over 2. So I'm going to do a change of variables such that I can let my phi here be equal to 0 at the fixed point. And now, doing this change of variables, I understand that phi dot is equal to theta dot. It's equal to omega minus a sine of theta of phi plus pi over 2. Excuse me. And then trigonometric identities give us that, well, this is just a shifted cosine wave. So we just have cosine of phi here. And then finally, I'm going to Taylor expand around the fixed point. And now the only reason I did this change of variables was so that I can center my Taylor expansion around 0. And so I get that phi dot is approximately omega minus a. And then I think we have 1 minus phi squared over 2. And then I'm going to have order of phi to the fourth here. And those terms I'm going to neglect, as we previously have seen. So these terms become negligible for a small enough phi. And so now I'm going to have phi dot is approximately omega minus a plus a phi squared over 2. So now I've basically reconstructed the normal form of my saddle node bifurcation. And to estimate the period spent in the bottleneck, I'm just going to take the integral from negative infinity to infinity of 1 over, well, I'll just put the d phi here, of omega minus a plus a phi squared over 2. Okay, and this integral is convergent because it converges with 1 over phi squared, right? And so the final result here of this integral, I'm not going to write it out. I'm just going to So I'll fast forward all the integration steps. It's like a trig substitution that you need to know, and I think it's like root r. Like I think the trig substitution is something like root r tangent of some other variable. So there's some trig substitution involved in this integral. I'm gonna do a Calc 3 series some other time, but this is not the time for that. So skipping forward, we just have a pi over root 2 over root omega 1 over root omega minus a. All right, and this is the approximation for the time spent in our bottleneck. Okay, so hope that was helpful. And I know this was kind of a short lecture. This chapter pretty much extends all of the same ideas we've been using, and we're just changing the domain to 2 pi periodic domain on the circle. It's going to be super useful for looking at higher dimensional systems in polar coordinates or in spherical coordinates. And so we'll find that knowing kind of how to analyze systems not only on the real line but also on a circle, um, both of those different ways of looking at a problem can be useful depending on the context of which coordinate system is most beneficial for us to use. And so next time we'll be delving into chapter 5, where we start with a two-dimensional system of differential equations, which is really exciting because now we can get into like motion where we have periodic motion on the real line. And so yeah, it's fascinating stuff. So I'll see you tomorrow.